Okay, let's do a takeaway from today. So today we talked about different parameterizations of a path. So here the path is not written as a parametric equation. It's written as a Cartesian equation. So just y as a function of x. So here, let's add a domain restriction. So here is y equals x squared for x greater than or equal to 0. Well, okay. If I want to turn this into a set of parametric equations, there's lots and lots of different ways to do that, and those are all called parameterizations of the path. So let's look at one really easy parameterization, and let's think about what kind of motion it has, and then we'll think about how could you make different sets of parametric equations, different parameterizations, and how is the motion going to be different. The path is always going to be the same because we're always parameterizing the same path. So the different equations are just going to be different movements along the path. Okay, well, if I want to take this equation and make an easy parameterization, I'll just say, let's say that my x-coordinates are always the same as time. So if I'm imagining a little table here, at time 0, 1, 2, 3, my x-coordinates will also be 0, 2, 1, 3. And that's just a decision I made. Okay, is it possible to have y-coordinates that still follow this path if my x-coordinates are time? And the answer is yeah. If the x-coordinates are the same as time, then the y-coordinates should just be time squared, which hopefully makes sense because squaring time is just like saying let's square the thing that my x-coordinate is, because my x-coordinate is the same as time. So for y's, I'd get 0, 1, 4, 9. So this is a very simple parameterization, and it works no matter what type of curve you want. You can always choose to say, I want my x-coordinates to just be the same as time, and my y-coordinates are going to be whatever function I want to apply to the x-coordinates. Okay, so what kind of motion does this have? So we know that at time equals 0, I'm sitting here, and then as time goes up, my x-coordinates are going up. So I must be moving in this direction. And more than that, you know that you're moving right at a constant speed, because as your time goes up by some amount, your x-coordinates go up by that exact same amount. So that means constant speed to the right. Okay, let's take a look at a different parameterization. What if I have x of t equals, oh, I don't know, let's do 4 minus t. And let's make this be 4 minus t. So first let's convince ourselves that this is actually the same path. One way of actually figuring out what the Cartesian equation for the path is was that thing that we learned, where you can solve it like a system of equations to figure out the Cartesian equation. Let's do that, but you'll see really soon that there's a much more direct thing that you could be spotting. So all I'm doing is rewriting it without the function notation. I'm going to go ahead and isolate t. So t equals x, what am I trying to do? 4 minus x. So I added t on both sides, I subtracted x on both sides. And now I'll substitute that in here for the value of t. So I've got y equals 4 minus my old value of t, which is 4 minus x, squared. Okay, let's simplify that all. So I'm going to apply the negative sign to the 4 and the negative x. So that gives me 4 minus 4 is 0. Opposite of negative x is positive x, and the squared is still there. So I've gotten y equals x squared. This was all a little bit silly. I mean, I wanted to go through the steps to show you that the thing that you knew how to do before still works. But there's a much more conceptual thing you can do. Remember that whatever this equation is on the right-hand side here, whatever number I plug in for t, the number that this purple blob ends up as, that's your x-coordinate. Notice that it's the same equation inside the purple blob. So whatever your whatever time you plug in, purple blob gives you your x-coordinate, and that's the exact thing I'm squaring to get the y-coordinate. So, I mean, you could even just do a substitution like this. I know that x is the same as 4 minus t, so saying that y is 4 minus t squared is just the same thing as saying y is x squared, because x is 4 minus t. So I just make that substitution straight in there. I don't need to isolate t at all. And in general, you can see that this kind of should always work. Here are several more parameterizations. I don't know what the motions look like. I mean, we could think about them. But here I have some equation for calculating the x-coordinate. And then I see I have that same equation squared. So it's like whatever my x-coordinate is, I'm squaring it to get y. Here's a different equation for x. I'm taking that same equation to square it to get y. So in all of these cases, it's going to simplify to just be y equals x squared, which I know is that path. So again, same path, but different motions along the path. So let's think about the different motions for a minute. Let's go back to this one up here with the 4 minus t. So a nice thing to do is to think about what's our position when time equals 0, and what happens as time increases. So here if I plug in time equals 0, I get 4, and then I know that the y coordinate is going to be 4 squared, so up here at 16. So here is t equals 0. Okay, what happens as t goes from 0 to 1 to 2 to 3? Let's just think about the x-coordinates first. I'll have 4 minus, so when t was 0, I had x-coordinate of 4. When t is 1, I'll have 4 minus 1 is 3. When t is 2, I'll have 4 minus 2 is 2. And in general, the larger t gets, the smaller x is going to get, because I have 4 minus a larger and larger and larger thing. I'll have 4, 3, 2, 1. So as time goes up, my x-coordinates are moving to the left at a constant rate. What are my y-coordinates doing? I don't even need to make a table, because I know that whatever my x-coordinate is, the y-coordinate is going to be the square of that. So I know here at 3 it's going to be 9, at 2 it's going to be 4, at 1 it's going to be 1. So I know it's always going to make that same y equals x squared path, only this time the motion is starting here and moving to the left. So that's the key insight. The key insight is if you want to control motion along a path, you can start with the Cartesian equation for the path. You get to choose whatever you want for your x equation. And you can think about, okay, what could my x equation be so that I'm at a particular x coordinate when time equals 0. In this one, I was moving right as time increased. In this one, I was moving left as time increased because I was subtracting the value of time from my x coordinate. So you can control where you start, and you can control are you headed left or right. Once you've chosen your x equation, you don't have any choice at all about your y equation if you want it to follow a particular path. Because once you have your x equation, you know that to produce y equals x squared, you'll have to take that same x equation and square it to get your y equation. Because what this shape literally means is a relationship between x coordinates and y coordinates, where the y coordinate is always the square of the x coordinate. And that's all this is saying. I'm saying take the x coordinate, square it to get the y coordinate. The only difference is the x coordinates have a particular process that will tell me where are they at different times. That's it. I hope that this was helpful.